of electromagnetism by a brief discussion on Maxwell's equations and electromagnetic waves. Now, if you know a couple of laws that we have talked about already, for example, Gauss's law and Ampere's rule, can you recall those two rules or laws? What is Gauss's law for electromagnetism? Gauss's law talks about the net flux that leaves a surface that encloses a certain amount of charge. It says the net flux equal to Q divided by epsilon naught, where Q is the amount of charge enclosed in that surface. Alright, Ampere's rule we discussed in the last lesson. Ampere's rule is about a conductor carrying a current, and if you take a closed path around it, well, the magnetic field in the direction of that closed path, if you take delta L, a small length element, and multiply that with the magnetic field in the direction of or parallel to that delta L, the product of delta L and the magnetic field parallel to it will be equal to the net current within that closed loop. That is the Ampere's rule. Well, both these rules are actually part of Maxwell's equations. So, let's now talk about Maxwell's equations. Well, according to Gauss's law for electric fields, the net electric flux leaving or entering a closed surface enclosing a charge Q is given by integral E dot dA equal to Q over epsilon naught. What does this quantity mean? EdA. Well, if you consider a surface, the E is the electric field at right angles to that surface, and dA is a very small area. So EdA is the flux leaving that element area, and if you integrate that over the surface, that is the net flux. So actually this is the quantity which we generally call the net flux leaving a surface, equal to the enclosed charge divided by epsilon naught, where what is epsilon naught? It's the permittivity of free space, and it has a value 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. Now, there are corresponding quantities in magnetism. Can you remember what is the corresponding quantity in magnetism for epsilon naught in electricity? Well, that is mu zero, which is the permeability of free space. So epsilon naught is the permittivity of free space, and remember its value, and mu zero is the permeability of free space. We will use all that in here. So this is the first Maxwell's equation, which is Gauss's law. Gauss's law is Maxwell's first equation. Now, Maxwell's second equation is a similar statement for the magnetic field. So there's a statement for electric field and a similar statement for magnetic field. How can you have a similar statement for magnetic field? Can you have a magnetic pole enclosed inside a surface? Well, you know that magnetic poles don't come in monopoles. They only come in the form of dipoles. So in this case the statement is a little tricky, isn't it? Since there are no free magnetic monopoles, a given space cannot enclose any magnetic monopoles. That means the amount of monopoles that is enclosed in any space will be zero. The amount of magnetic flux entering a closed surface must be equal to the amount of flux leaving it. Therefore, how would you define the second law, second Maxwell's equation, which is analogous to the Coulomb's law in electricity. If you translate that into magnetism, it becomes the second law of Maxwell. Therefore, the net flux out of the enclosed volume is zero. Why is it zero? Because the net poles, monopoles enclosed in that surface is zero. And therefore, the second Maxwell's equation is integral B dA. What does B dA stands for? Well, B dA is the flux that leaves a small area dA, and you integrate it over the entire surface. That is the net magnetic flux leaving that surface, and that is equal to zero, is Maxwell's second equation. Now you notice that Maxwell's first and second equations involve integration over a surface. In other words, the total flux that leaves a surface. Now the first two Maxwell's equations given above are for integrals of the electric and magnetic fields over closed surfaces enclosing a volume. That we just talked about. The third and fourth Maxwell's equations are for integrals of electric and magnetic fields around a closed curve. Well, are you familiar with integrating around a closed curve? We just talked about it. Ampere's rule. If you have a closed path around a conductor, we said the product of the length element delta L times the magnetic field parallel to it. And if you add up all such quantities, and that is what we call the line integral, integral around a path. So the third and fourth Maxwell's equations are for integrals of electric and magnetic fields in closed curves. Now, we take the component of the field pointing along the curve. Now, that is very important. If I can find a curve, let me see if I can find a curve. Now, here is an example of a closed path. If I take a small element of this delta L and multiply that with the component of the magnetic field in the direction of it and add all such products along the length, that is the line integral, total line integral. So we take the component of the field pointing in the direction along the curve and calculating the line integral in order to calculate EdL or BdL. In the case of the electric field, we take the component of the electric field along dl. In the case of the magnetic field, we have the magnetic field along dl. So we have EdL or BdL and integrate it along the curve, and that is the quantity we will be using to describe the third and fourth of Maxwell's equations. Now, these line integrals represent the work that would be needed to take a charge around a closed curve. Well, so EdL is a measure of work done to take a unit charge around this closed path. Alright. Now, the simplest version of Maxwell's third equation is the electrostatic case integral. Now, remember, this integral stands for the line integral. The earlier two integrals we did for equations 1 and 2 are surface integrals. So, line integrals E dot dl equal to 0. In other words, this is the equation similar to Ampere's rule in magnetism. And this is Maxwell's third equation. And a similar line integral in a magnetic field is the Ampere's rule, which we talked about. In other words, delta L times B integrated along the length of the curve is a measure of the amount of current inside the loop. So the magnetic field in a space around an electric current, the magnetic field in a space around an electric current is proportional to the electric current which serves as its source. In fact, the magnetic field is actually created by the current in this conductor, just as the electric field in space is proportional to the electric charge which serves as its source. Now, Ampere's law states that for any closed loop path, that's a closed loop path, the sum of the length elements times the magnetic field in the direction of the length element. One more time, if you take that length element delta L and take the component of that B in the direction of that delta L and multiply the two, B delta L, and integrate it along the closed curve, it will be equal to the permeability times the electric current enclosed in the loop. The electric current enclosed in the loop will be I. And we write it like this: line integral B dl is mu0 times the net current within the loop. And that is the fourth Maxwell's equations. So here, I net is the net current passing through the surface bounded by this closed path. Alright, however, this equation requires a little more